We'll start down by writing down steady, incompressible 2D Navier-Stokes equations. Okay. So the x momentum equation. So I'll throw away the unsteady term. U dou u by dou x plus v dou u by dou y equal to minus dou p by dou x plus mu del square u by del x square plus del square u by del y square rho u dou p by dou x plus v dou p by dou y equal to minus dou p by dou y plus mu L square v by L square plus L square v by L square. Okay, so these are the equations that you should have really solved to get velocity profile inside the boundary layer. Okay, I'm going to make some assumptions which is basically on the fact that if you go to higher and higher Reynolds number, the boundary layer is supposed to be very thin. Okay, it's going to get smaller and smaller and smaller. And also you know that the largest velocity, okay, is in the u direction. In other words, the v velocity is going to be much smaller than u. Okay, so I'll say, okay, if my v is much smaller than u, and if I say my dou u by dou x is much smaller than dou u by dou y, because dou u y is a small number, okay, dou u by dou y is going to change from 0 to some finite number in a small thickness, but dou u by dou x is what? The change in u along x, okay, which is changing very slowly. Okay, so therefore this approximation of dou u by dou x is smaller than dou u by dou y is good for boundary layer. Also dou v by dou x is much smaller than dou v by dou y. Okay, so these three approximations are found to be good for a boundary layer if the boundary layer is very thin. And if I use that, and if I look at my y momentum equation, I find that this quantity has a dou v by dou x in it. This quantity has a v times dou v by dou y. This is also proportional to v. This is also, proportional to v. In other words, this equation, okay, this left hand side, all I am drawing it in this circle, okay, are going to be extremely small quantities for a boundary layer. Now you have to trust me there, because one has to actually do a formal way of doing it, and I'm sort of going to tell that that's what is going to hold for the boundary layer. Okay, and the reason I want to tell it is because if you look at this entire equation, any of these terms will come out to be so small that you essentially end up with this expression that dou p by dou y is going to be 0. Okay, or in other words, pressure variation across the boundary layer is a small number, or it's actually negligibly small. And so in other words, therefore pressure variation is only in the x direction. Okay, it's not there in the y direction inside a boundary layer. Or to put it physically, if you have let's say we have a diverging channel, okay, and let's say you have a fluid that's coming and a boundary layer is growing. Okay, so this is boundary layer. Okay, so that was our so let's say we have two plates, okay, diverging, and there is a fluid that's coming, and let's say boundary layer starts growing on the solid wall. Okay, because you have fluid coming and is going inside a diverging channel, what happens to the velocity? Velocity will decrease, right? So that would mean pressure would increase. Okay, So you can really apply Bernoulli's equation and let's say calculate pressure here and pressure here. Okay, you can use the same pressure here also, because the pressure variation inside a boundary layer is going to, across the boundary layer is so small. Okay, the pressure variation along the boundary layer is then determined by what is happening outside. If pressure was changing with respect to y, then you would have to worry about, okay, how does the pressure change? But if you want to only determine pressure inside the boundary layer, okay, you can actually calculate it from the numbers that's not outside. I have given a very sort of hand waving arguments. If you don't believe it, just don't worry, but take it for granted that pressure variation across the boundary layer is going to be so small. Therefore, you can actually determine the pressure variation inside a boundary layer just by knowing the pressure outside. Yeah. This is in laminar, meaning laminar boundary layer. No. So there we are basically saying that the pressure variation is only in x direction, right? No, there we can actually show that, right? So there what happens is, if you look at the v velocity, all of them will identically go to 0, and therefore we will see that dou p by dou y is 0, and therefore p is not a function of y. Now I know that v is not 0, so none of the terms are actually 0, but they are all small. So in other words, the flow is going to be very similar to what you will have in your pipe flow. Okay, v component is very small, that you will basically end up with a similar situation where p with y variation is going to be small. So the situation is similar. So you can see the analogy already, that it's because of the reason that v is very small that you are ending up with such a conclusion. Questions? Okay. So that would mean that this quantity dou p by dou x is simply dp by dx. Okay. So I'll write down my x momentum equation again. My x momentum equation is going to be rho times u dou u by dou x plus v dou u by dou y is equal to minus dp by dx plus mu del square u by del x square. Del square u by del y square. So I am not writing del square u by del x square, but del square u by del x square is also expected to be very small. Okay. And the only reason I want to write it down is because I want to write this equation on the surface of a or on the wall. I want to simplify this on the wall. So what is u on the wall? 0. What is v on the wall? 0. Okay, so u is 0, v is 0, and therefore if I actually look at my x momentum equations, these things go away on the surface of the wall, and therefore I actually have mu d square u by dy square is equal to dp by dx on the surface. Okay, all of you agree? Okay, pressure is decreasing with x. So what is the situation that I am going to look at? I am looking at this kind of a diverging channel. Oh no, I don't want to do that. I want to start with the other one. Let's look at converging channel. So velocity decreases, pressure increases. So dp by dx is greater than 0. Okay, so let's say we have a converging channel. Okay, in the converging channel, velocity decreases. That would mean pressure increases. So if I have a boundary layer, so let's say you have a kind of a converging channel. There's a fluid that's coming and going. So if there is a growth of boundary layer like that, Okay, I'm basically looking at a point somewhere there and trying to write down what is it. Okay, what does the differential form telling me? So I have taken a situation where dp by dx is greater than 0. Yeah, your question. So let's say you have, so far we have been talking about a flat plate and a fluid that's coming, right? Now, and we said, of course, the outside the boundary layer, the fluid is moving with a constant velocity. Okay. Now I am expanding that case to which the outside fluid is also either accelerating or decelerating. So the u infinity that I have been having, okay, I'm looking at it as an accelerating fluid or a decelerating fluid. So it will accelerate or decelerate. I mean, to accelerate or decelerate, I'm trying to put it in a converging or a diverging channel. So I have a uniform flow that comes and then it is seeing a converging section. So it's basically going to enter that converging section. While it is entering the converging section, it's basically going to see, it is going to develop a boundary layer. Okay, as if it's like going to have an entrance length. Okay, so it's going to develop a boundary layer, and I also said, look, if I look at the pressure gradient outside, that's going to be same as the pressure gradient inside also. Okay, the dp by dx inside the boundary layer is same as dp by dx outside the boundary layer. So if I simply apply my Bernoulli's equation, which is the fact that the velocity is increasing, I would see that my pressure is decreasing if it's a converging, otherwise it's increasing in a diverging channel. Okay, so just by looking at whether u infinity is increasing or decreasing, I am able to tell what is going to happen for the pressure inside the boundary layer, and by looking at that, I am actually going to now predict what is going to be the flow profile exactly on the wall. So so what am I'm going to first look at cases where it is a converging channel. So u in is smaller than u out. So that would mean P in is greater than P out, and therefore dp by dx should be less than 0. Correct, in a converging channel? So I'm again making a mistake. dp by dx is less than 0 is the first situation that we will look at, which also would mean du by dx. So u is increasing with u is increasing with x. So du by dx is u is increasing with x. Du by dx is greater than 0. Okay, so we said on the surface, this is the expression that should hold. Okay, so if I have a situation in which dp by dx is less than 0, my d square u by dy square should also be negative. So if my d square u by dy square is negative, can we tell what the velocity profile should be? Should it be like that? Should it be like this? Should it be like that? Maybe I draw 3 different colors. Should it be like this? Should it be like that? Or should it be like this? Remember, this expression that we have written down is valid only at the wall. So I can only tell how it should be at the wall. But by looking at this, where I have dp by dx less than 0, that means d square u by dy square less than 0. Whether this green or blue or this magenta will satisfy d square u by dy square less than 0. Green can't, blue can't, because blue means it's a straight line. So the second derivative should go to 0. So blue is ruled out. Now green or magenta. How do you know that? So let's say d square u by dy square. I'll write using finite difference approximation du by dy at y plus delta y minus du by dy at y divided by delta y, right, in the limit of delta y going to 0. I want d square u by dy square to be less than 0. So that means du by dy at y plus delta y should be smaller than du by dy at y. Okay, so du by dy is the slope, and that slope should be largest at the wall. So that is satisfied by the magenta line, right? Remember, u is on the x-axis, y is on the y-axis, okay? So when I say du by dy, you should really be looking at the slope like that, okay? So it's highest like this. So it's a magenta line that's going to be satisfying this situation, d square u by dy square is less than 0, okay? So I can immediately say that therefore the green can't be, and it should be something like the magenta, okay? So this is what the boundary velocity profile should be if I say dp by dx is less than 0. Okay, so what should happen is that the profile would, and that's what we have drawn, and that's what we had analyzed also. So it's essentially going to be something of that sort. Yeah. Yes. Come here, du by dx, you're arguing du by dx is not small. I'm saying that du by dx is going to be smaller than du by dy. Okay, because u changes from 0 to capital U in a small distance of y, while u will be changing very slowly along the x direction. So it has to be a sort of a slowly converging. It can't be like that. It has to be something where this approximation holds. True. So that's because we can't solve the actual equation. So we are saying, okay, can we actually simplify it in some way so that we can get some qualitative arguments, and then which might true hold in a general situation, and that's what we are trying to aim at. Okay, so this situation is called a favorable pressure gradient. We'll see why it's favorable later. Let's call that favorable pressure gradient. Okay. So the next one we want to analyze is dp by dx is equal to 0. So that was case 1. Case 2. dp by dx equal to 0, what would be the profile? We know dp by dx is given by, so d square u by dy square, the curvature is 0. So the velocity at the wall should be linear. Okay. So it should start linear, but then we don't know what is going to happen, something of that sort. Okay, that's going to be if dp by dx is equal to 0. And if dp by dx is equal to 0, what would you say about du by dx, the outside velocity, du infinity if you like. Du infinity by dx is also 0. Okay, so outside fluid is not changing its velocity in any fashion. Pressure is also not changing. So see here, if you look at this would be linear, but then we do not know because this equation holds true only on the surface. Right, this equation is not completely general. We got it when we put u is equal to 0, v is equal to 0 in the conservation equation. Okay, in the full equation we put u equal to 0, v equal to 0, threw away these terms, and therefore we got this. So that can hold only on the surface of the wall. Yes, this is only for the thin boundary layer. Yes, if the so because we are saying that dp by dx, right, we can say that it's only a function of outside when the boundary layer is so thin, so that we can neglect all all x gradients and so on. And typically boundary layers are thin, like it may be like a millimeter or smaller and things like that. On the surface y equal to 0. Yes. On the surface y is equal to 0, u and v are also 0, right? Yes. So let me just tell you again. So see, by looking at the v momentum equation, okay, whether you believed me or not, what I said is that pressure, okay, across the boundary layer, pressure in y direction is not changing, okay. That means pressure in x direction is the only thing that is changing. So if I have a boundary layer and outside the boundary layer, if I know how pressure is changing, I will know how pressure changes inside the boundary layer also, because pressure does not change in the y direction. Is that clear? Okay, you have a boundary layer. Okay, let's say this is the plate. You have a boundary layer. The boundary layer is very thin. I am saying that pressure variation across the boundary layer is very small. That means if I know pressure gradient outside, I will know pressure gradient inside also. If it is 1 atmosphere, 1.5 atmosphere, it will be 1 atmosphere and 1.5 atmosphere inside also, because I know pressure is not changing across y. Okay, knowing a pressure gradient outside will help me to tell what is pressure gradient inside also in the boundary layer. That's the first thing that I said. Second thing I have said is, if I look at the x momentum equation and if I write down the x momentum equation on the wall, okay, on the wall, then I know because of no slip and no penetration, my u component of velocity is 0 on the wall, my v component of velocity is 0 on the wall, and therefore I am able to simplify my governing equation into this magenta circle, okay, where I have only a viscous term and a pressure term. Okay, now remember that pressure term dP by dx, I say I already know it from the external flow field. When I say external, this is external to the boundary layer. So by knowing what is the pressure gradient outside, I can tell something about my velocity profile on the wall. That's where I am doing really. Okay, by knowing the pressure gradient outside, I am able to tell something about my velocity gradient on the wall. Is that clear? Does that answer your question? What is your question? Turbulent. Yes, it's only on the surface. So remember, I am drawing it only on the surface, okay? So when I said, d square u by dy square is less than 0, I only know it at this region. When I am saying d square u by dy square is 0, I only know about this. Okay, the other part I just connected and drew. I do not know what it is. And I am not going to care about that also at the moment. This is wall. The other is just to draw the profile. I am just drawing it from 0 distance. Yeah, because I have pressure decreasing, so velocity increasing. So this is only up to boundary layer. Whatever I have drawn is up to bound. So delta is going to be much larger than that. Okay. So let's say. Okay. So this distance up to which I have drawn is really inside the boundary layer. It's not even going to connect outside. See, I can't say even anything because I am really looking at wall. What is the governing equation at the wall and making some deductions. It will be actually continuous because it's increasing and it will go and then join there, and outside then outside again there could be some changes which will be along x direction, not along y direction. This one at y is equal to 0. You have some doubts? No. Okay, so then if I have a case where dp by dx is less than 0, in fact all three cases are going to be dp by dx less than 0. Okay, what do we know about d square u by dy square at the wall? Should be greater than 0. Correct? So that means my curvature can't be like this. My curvature should change the sign. So initially it was like this. Then I said it's going to be like this. Now it has to be like that. Okay. So in other words, my velocity profile should start doing that. Okay. The original one of those color, green or magenta, that we had wrote it wrong. So like that, and then it would do that. Sign d square u by dy square should be greater than 0. Okay, so write it down again using your finite difference and see. Remember, u is your x-axis, y is your y-axis. Okay, so it's typically opposite to the slope that we talk about. So, correct. Sorry, that is right. Yeah. Okay, so this is what the velocity profile going to be if I have. So when would this happen? This would happen when dp by dx is greater than 0. That means pressure increases along the x direction. That would happen when u decreases along the x direction. U will decrease along the x direction when it is a diverging section. Okay, so if you have a diverging section, then you should expect the velocity profile to curve in a different way. Is that okay? So if dp by dx is even larger, what would you expect? This curvature would increase at the wall. It would almost become flat and do that. If dp by dx is much larger, it would even bulge more and it would actually do that inside the boundary layer. I am drawing my u velocity. What does the last figure tell? That on the wall, the flow is actually in the opposite direction. If dp by dx is very large, so this is dp by dx is small. Let's say this is some moderate and this is some large. Okay, so if outside fluid, outside the boundary layer, if pressure increases, okay, and if that pressure increases very large, on the wall, the fluid will actually start flowing in the opposite direction. Okay, that's what we actually called flow separation. So whenever we talked about, those diverging sections and so on, I always drew fluid flowing in the opposite direction, right? So this is because of this particular reason, okay? This is called actually boundary layer separation. Okay, the external pressure gradient will cause a fluid flow to have, flow in the opposite direction on the wall.